There we go. All right, are there any questions before we start?
There we go.
All right, a couple announcements. Today's lab is a review session. We'll talk about anything you want to talk about. Bring your questions. I'll open up lab by saying, are there any questions? And we can spend this time to go over additional examples, talk about interpretation, explanation, anything you want. So come with your questions to lab today, and then we'll do the same thing on Monday for Monday's lab. And then right after Monday, we'll hand out the exam.
So do we go to our respective lab sessions then, or should we go to both?
Go to your respective lab sessions, yeah. Especially if you have questions. So there's no reason why you couldn't attend both labs. And it's no problem if you want to go to 2 review sessions. The only concern, but I don't even think it would be a concern, would be that for people in their assigned lab, if everybody showed up at one or the other, if people who were assigned to their lab didn't have an opportunity to ask questions because there were so many. But I honestly don't think that will be an issue. If we start to run out of time on one of them, I might say hold your questions for your assigned lab period. So if you, just to put a point on that, if you're in today's lab and you have questions, come and ask them today, but feel free to join Monday. And if you're in Monday's lab and you have questions, ask them on Monday, but feel free to join today's lab. All right, then let's get started with population analysis. So we left off talking about several methods for estimating population sizes, kind of high-level methods. And the main question is, how do we estimate abundance or population size? This is important for many reasons. We talked about these. We talked about the BIDE model. And we talked about how we can use this information to inform management. There are 5 methods listed here, ranging from complete census to removal method. Last Monday, we talked about complete census and plot sampling. Today, we're going to continue on distance sampling. Then we'll talk about marker capture methods. The good news is distance sampling is very similar to methods that we have already learned about, mainly binomial regression or Bernoulli regression. All right, so when do we use distance sampling? The premise behind distance sampling is you sit from a fixed area, you have a survey area of a known distance that goes out in either direction of you if you're on a transect, or in 360 degrees if you're sitting at a point doing a point count. And actually, it doesn't have to be 360 degrees. It can be whatever angles you want, as long as you know that in advance and you can specify that. So here's a survey, one method used for one application which distance method is used. If someone's driving along transects and they're counting the number of deer, they can use a rangefinder to figure out how far away the animal is. One of the assumptions of distance sampling is that you know exactly how far away an animal is from a line. So there's a number of ways to do that. You can use technological devices like rangefinders to get those distances. You can use reference points if you see an animal and mark it and then measure it later. And you can use other things like angles and distance, and calculate the distances using trigonometry. Distance sampling is common in aerial surveys where you can use marks on wing struts to identify how far animals are away. This puts animals into categories by looking where they are. So if you're counting animals over this area, this is for goose surveys, I believe, where if it falls within these strut lines here, it's a certain distance, here's a certain distance, and so on. And we can determine what those distances are, again, using trigonometry and the angles to these points. and knowing the known height of the flying distance. Just another example of what these are used. And in fact, you don't actually have to be surveying animals for distance. You can survey signs of animals, and then you can estimate the number of signs of animals. So we have some scat on a log here that we can examine. So if we're walking through the forest looking for moose, maybe moose are hard to find, but we can look at moose droppings and use that as a proxy for the animal. All right, so what's the modeling behind distance sampling? Well, it's close to what we've already seen. The only difference is we're estimating a different parameter. So think back to a Bernoulli trial. Remember, this is just like flipping a coin. And if we're flipping a coin, the probability of success is 0.5. Whether it's heads or tails, or 0 or 1 is a y value again. And then we can add covariates and parameter values by using this logit link function. And then we have our beta 0 parameter here. Our beta 0 is different than our probability of success p. In this case, p equals 0.5. And if we did our inverse transformation here, we'd figure out that when p equals 0.5, beta 0 equals 0. Now we're gonna talk about going from a Bernoulli distribution to a binomial distribution, and making that transition is very straightforward. Instead of doing one coin flip and saying whether we received a 0 or a 1, a heads or a tails, we're going to do, the analogy is we're going to do 10 coin flips, and we're going to count how many successes there were. So how many heads there were. But the probability of success is measured in exactly the same way. All right, so now our data are not zeros or ones, but they are values between 0 and how many trials we do. So in this example, if we did 10 coin flips, our y can be anywhere between 0 and 10. So we can have 0 heads, or we could have 10 heads out of 10 coin flips. And if our probability of success is 0.5, we would expect on average that we would have 5 heads in that. All right, so back to our example we talked about on Monday, where we have these strips of known length and known width. We walk along these strips, and now we're dropping the assumption that we assume we see every individual within our strip width. We're going to allow our data to have missing values. So here's the scenario. We walk along these transects, starting here, going up, and then continuing down. We know how long our transects are, and with each of our transect, we measure where the animal was seen and how far it was seen away from the line. And we keep track of each individual we see and how far we see away from the line. And how far away it is from the line is going to provide us enough information to tell us about how many we detect on average, given all of them are there, with a couple assumptions. So the red ones are ones that we're seeing. We can see this one is really close to the line. We see this one is a little further away from the line, and we missed that one. It's not colored red, so we didn't see it. It was truly there, but we missed it. And this is called an error in our data collection. It's called a false negative error, meaning we failed to detect it when it was truly there. And then similar data types for all of these. So we go through this survey and we count all of the we keep track of all the distances, both how many there were that we saw and the distance they were from the line. And that's going to give us some information that we're going to use to estimate P. But before we get into actually estimating what the detection probability or probability of success P is, let's talk about how we could use this information to estimate how many of the total dots there are within this area, given our counts. So for now, let's assume that we know what the detection probability is. So maybe we did a study previously and we know on average we detect about 70% of the animals that are truly within our transects. So we're going to say our expected probability of success, mu, equals 0.7 in this example. Now this should look vaguely familiar to what we've already done. We can compare it to the previous slide, where we have yi comes from a Bernoulli distribution with probability of success 0.5. when we extend that to the binomial distribution, we have yi comes from a binomial distribution with probability of success 0.5. And then the total number of trials is 10. When we go to distance sampling, if we assume we know the probability of success and we know how many we actually counted within our strips, the thing that we don't know now is n, the total number of trials. And that's what we want to estimate. So this problem is very similar to what we've already talked about. Before we knew y, and we knew the number of successes, and we tried to estimate the probability of success, mu I. Now, if we know mu I, and we know y, can we estimate what n is? And n is going to be the total number of animals within our transects for this example now, and later we'll extend that to the total number of animals within the entire survey area. All right. So here's the scenario. In these strips, the number of red dots are 68. We saw 68 animals. We know that we only saw about 70% or 0.7 of the animals in the transect. So let's figure out how many there are total within our transects. The easy way to do that is to take the number we saw and divide it by our detection probability, 0.7. And when we make this calculation here, it tells us there were about 97.1 numbers there within our transects. So our probability of success, or the detection probability, equals 0.7. We started off knowing this information. Later, we're going to talk about how we estimate this information when we don't know it. The transect covered 1,000 of 5,000 total area. So the total area in our box here is 5,000, 50 by 100. And in the green areas covered only 1,000 of that, so roughly 20% of the study region. Now, given that we observed that there were 97.1 animals in our transects, we didn't observe this, we estimated 97.1. We saw 68. We know we see about 0.7 of the animals on average. So from that, we can figure out there are 97.1 animals total within our transects. And then we divide that by the proportion of the study area we covered to get 485.7 animals within the study area. Here are those calculations. We can do these and get our total estimate for the number of animals. All right, so we'll come back to this, but what are we missing from this estimate? We estimated how many there are. What's missing from that estimate?
The distance that they are from.
That's true. Yeah, that's a good point. That's it's exactly right. It's not exactly what I was thinking, but that's right. And we'll talk about that in the next couple slides. Yeah. So this goes back to statistics in general. And remember, the field of statistics is about describing uncertainty. So we made an estimate here. And what we lack right here, and we'll come back to later, is an estimate of uncertainty on that estimate. Maybe a 95% confidence interval around that estimate. So we estimated that there were 487 animals, but what we haven't said yet is how certain we are about that estimate. And we usually use 95% confidence intervals to describe that. And we'll come back to confidence intervals in another lecture. The nice thing is the software that we're going to use provides those information for us.
I have a question.
Right. Yeah, please.
So we were talking about plot sampling versus like distance sampling and stuff, and it seems like the main assumption difference is that like you're assuming that you're seeing all of the animals in your transect in plot sampling, and I was just wondering like what are the advantages to using like plot sampling over distance sampling, and like when would you use one over the other?
Yeah, good question. Let me go back here. All right, so if, let's look at what plot sampling is in terms of our model. Let's see, where's our model here? Our model is, here's the model we're using right here. Right, so we have our counts of animals within our plots. We have the total number of animals, and then we have our detection probability. Plot sampling is the exact same thing as distance sampling, except we assume that this number equals 1. We assume the probability of detection equals 1. So if you know that you're going to see all of the animals, then plot sampling will give you more precise estimates of your abundance. You'll get a better estimate of N if you can assume that you're going to see all of the animals. If you know that you're not going to see all of the animals, or you know that there's a chance you won't see all the animals, you want to estimate how many you'll miss. Because if you don't allow for this, allowing the probability of success to be less than 1, then what's going to happen is you're going to assume you're seeing all the animals that are out there, even though you're going to miss some, and your estimates are going to be biased low.
Okay,
You're going to undercount how many animals are out there.
thanks.
Yep. All right. So here's what, now going back to the comment about the distances and keeping track of the distance. So here's a video of someone walking along surveys, and they see some of the animals within their transects, and they don't see all of them. And when they see them, they record the distances. The assumption of distance sampling and the methods that we use is that we can estimate the detection probability, how many we miss on average, if we can assume that we see all animals that are directly on the transect. So all animals that are right on the line, for example, this one right here is right on the line. Our assumption is that if that animal is there, that we're going to see it. And what's showing up here on the right is a plot of the distances and how many animals we saw within these bin widths here. So as we get further and further away, the assumption is we're going to see less and less animals because they're farther away, they're harder to see. And the assumption is that if they're directly on the line, we're going to see them. So there are some cases where this holds really well, and there are some cases where this doesn't hold at all. So one case where it holds well is if you're flying transects, you're moving pretty quick over an area where the animals are visible. The animals are visible right underneath you. So if you're doing maybe an elephant survey in the plains and there's not a lot of cover and you're flying over an area, if there's an elephant there, maybe you can design this aerial survey so that if it's under you, you will see it. Methods where it doesn't work so well. Suppose you're driving on a boat, and whenever you get close to an animal, you're driving up to it, it dives underwater, and it makes it hard to see. So the assumption with distance sampling is that if it's on the line, you detect it with probability equal to 1. And if you can meet that assumption, you can use distance sampling to estimate your probability of seeing an animal. All right, so how do we estimate our detection probability P from the data that we have? The idea then is if we assume that we see all animals right on the line, so here's the perpendicular distance from the line, and as you get further away from the line, you see less and less animals, and this should show up in your data. You should be able to plot a histogram of the distances of your data and see the black lines here. It should look something like this. It starts off high, and then it drops off. If we assume we see everything on the line, we can assume the detection probability equals 1 here. We see everything perfectly. And then we can develop a function that decays as the distance increases. And this function can represent our detection probability. Now, how do we actually estimate distance? Well, after we draw this line, after we estimate, so this line is analogous to the mu value that we have already talked about in linear regression. It's slightly different, but it's still a function. It's a function of distance, and it's going to contain parameters that are going to describe the best fit of this line. So we're going to tell it the form of the line, and then we're going to use the data to estimate the shape of this line. And this line is going to be the probability of success for any distance we are from an animal. And it has to intercept the y value when x equals 0 at 1. When we do that, we can calculate the area under this curve, and we can calculate the total area, and then we can divide the area under the curve, the area under the red line, by the area under the blue rectangle. And that'll give us the overall estimated detection probability. All right, so we can estimate the area under the curve. We could do something like a Riemann sum, where 0.25 is the width of each box here. So we have 0.25 is the width of each one of these boxes. There's 2 units here, could be kilometers, and we see that there are 8 different boxes, so 0.25 is the width. And then we can multiply that by the height of all of our curves at the center of the boxes, or at the center of the red line. And we figure out that equals 17, and then we can estimate the area under the triangle. The area under this triangle is just the length times the width. So we have 12 times 2 equals 24, and then 17 over 24 gives us our estimated detection probability of 0.7. So on average, we're seeing about 70% of the animals, or our probability of success of seeing an animal in our transect is 0.7. All right, so we talked about this curve. Now, how do we actually choose this curve? This is directly analogous to our model selection procedures that we've already talked about in using AIC, where we give it our data and we try and choose a line that maximizes model fit and minimizes complexity. And we can give it a bunch of different lines and see which one best fits the data. What do I mean by different lines? Well, I'll talk about those in the next slides here. We've already talked about a few mathematical functions. We've talked about the equation of a line, where we have beta 0 equals beta 1 plus x. A polynomial, which is a bendy line, where we have beta 0 plus beta 1x plus beta 2 times x squared. Now let's talk about a few more, the ones that are used for estimating distance functions. All right, so in our next slides, x is going to represent the distance from our observer. That's our covariate in these lines this time. Our function of x is going to represent the detection probability at a distance x. And to align this with our previous notation, if we just change this notation that's used in calculus f of x, where x is distance and f is our function, let's change f to p and represent our probability of success, or our detection probability at any distance d. So x goes to d and f goes to p, and then we'll have probability, our function is p of d. All right, so let's look at those functions here. The first function that we might consider is just a uniform function. The next one's half normal, third is hazard rate, and then fourth is negative exponential. The uniform function is the simplest, and it just assumes detection probability equals 1, no matter how far away we are from the line. So this goes back to Faith's comment about what's the difference between using distance sampling and a plot survey. Well, actually a plot survey is just a specific type of distance sampling where we assume the detection function is uniform and doesn't matter how far away the animal is from the line, we're always going to see it with probability 1. What about the half normal? Half normal looks something like this. If you imagine a normal curve, the bell-shaped curve, this is just the half of it, the positive side of it. And there's one parameter in our half normal curve, and that is sigma squared. So this is very similar to what we've talked about with normal regression, where we try and estimate sigma, and sigma sigma represented the spread of the data. The same idea is true here, where as sigma gets larger, this detection function gets more and more spread out, and we can cover a larger area. So if we use the half normal function, remember the idea here is we're trying to choose a function here, one of these lines, or this line, to match to our data right here. We're trying to match the red line to our data, and we're going to give our program a bunch of different lines, and it's going to choose the one that's best for us using AIC. So uniform is one line, half normal is one line. Now there's lots of different shapes that the half normal can take, and they all depend on the value of sigma, which is the parameter that we're going to estimate. They all have this general half bell-shaped looking curve, but how spread out it is depends on the value of sigma. All right, how about the hazard rate? Well, the hazard rate looks slightly different than the half normal. It has this larger elbow here, or larger shoulder here, and then drops off more steeply. And with our hazard rate function, there's going to be two parameters. There's going to be both sigma and beta. Here's what those functions look like. We have sigma here, and then beta up here. So this is the function that represents this line, and if we give it different values of sigma and beta, this function looks slightly different. And then lastly is negative exponential. Negative exponential is a very steep drop-off, and then decays as distance increases. So what scenarios might these functions represent? Well, negative exponential means we see all the animals right on the line, but as we take a slight step away from the line, our detection probability drops dramatically. So if this red line was our detection function, if we are 1/10 away from the line, 1/10 of a unit, maybe 1/10 of a kilometer, let's say, then our detection probability drops from seeing all of the animals to seeing only about 50% of the animals. So this describes how many of the animals we see as we get further and further away from the line. Now, something like this, we can see all of the, if we use a hazard rate function, we can see all of the animals for a pretty good distance, but then all of a sudden it drops pretty dramatically down, depending on the parameterization. And here we have a normal looking shape where it decays normally. So the question then is, which one should we use? And the answer is, this is exactly the same as our model selection question we asked before when we had lots of competing models and we use AIC to choose the best model. We want to choose the best model, and that depends on the data, and we want a parsimonious function so we can tell our program that we want to consider all of these models, and let's use AIC to choose the best detection function. And once we have that detection function, we can estimate how many animals we see on average, not only in our transects, but for any given distance away from our survey. It depends on how many parameters there are. The null model had 0 parameters, assumed constant detection. Half normal had 1. The hazard rate has the most parameters, with k equal to 2, and negative exponential has 1 parameter. So this is a model selection problem, and we've talked about addressing this a lot in all of our labs. All right, any questions? This is the end of our lecture for today. It's a short lecture. There is a, yeah, I'll just say that.
I do actually have some questions on the lab, not the lecture.
Okay, let me hold on to those just for a second, Brianna, and if there's no questions on the lecture, we'll jump right into that. Who's heard of distance sampling? A few people. Yeah, it's a very popular technique. And actually, the reason this lecture is shorter than normal, 20 minutes shorter than others, the Wildlife Society annual meeting is going on right now, and at 9:30 is the biometrics working group is having their annual meeting starting now. And I'm a board member of the biometrics working group. And we have to present the kind of, I guess it's like a lifetime achievement award for someone who received it. One of the nominees this year for that award was one of the groups in St. Andrews who developed distance sampling, and for all of their work on distance sampling, because it's been extremely important for estimating abundances in wildlife. We won't be using distance sampling on the exam because we haven't talked about fitting those models. But we'll talk about fitting. Go ahead.
Sorry, were you going to post links to like the presentations or whatever that you and Julia would be giving?
Yeah, we can do that. Certainly. Yep. I'll put those on. I'll put a link in Web Campus, but they'll be posted on YouTube. I'll post mine. Julie, are you going to post yours?
Yeah, I can do that.
Okay, sounds good. And actually, my talk is on regression methods, asymmetric regression, and actually a lot of the concepts will be pretty familiar to what we've been talking about in class. Okay, so Brianna, do you want to jump into your question on the lab?
Yeah. So this was looking at the hypotheses. How do we write one for the categorical? Because it's got so many parameters to it now.
Well, right. So with your hypotheses, you're talking about just explaining the hypotheses?
Yeah, for like categorical time, which has 22 parameters. How do you make hypotheses for that?
Well, the underlying hypothesis behind that is actually much simpler than how complex the model is. The reason the model is so complex is just because we have so many years of data. But the underlying hypothesis for that model is we think that sea otter abundance changes each year. And we can't necessarily describe that change by a linear trend. We don't know exactly why it changes every year, but we suspect that it's pretty stochastic. And from year to year, you're going to have pretty big differences in changes. And those changes may not necessarily be growing or declining.
Okay, that makes sense.
And then you'll want to support those hypotheses from other studies of other animals who have experienced similar types of scenarios.
One more quick question.
Sure, go ahead.
So on the plot, how do you name the X and Y axes?
Yeah, so one of the parameter settings in plot, if you do plot, open parentheses, close parentheses, and then you put in your X and Y. If you do comma, X lab, X LAB equals, and then you have to put quotes, and then you put whatever you want to name it in those quotes.
Okay, so
let me just put that in the chat here. So if I did
lab quotes. Okay.
Okay, so I put it in the chat box with that exact command you would use for X label and Y label. As long as it didn't autocorrect, it should be good.
Okay, thank you.
Yep. And a lot of those settings are people have spent a lot of time writing about those on Google too. So if you ever have questions like that and you don't have time to wait for office hours or something, you can find those on Google. But
So
I'm happy
Barry,
to,
I'll let
I'll
you-
go ahead. I say, but I'm
Um,
happy to talk about plotting commands too.
So just to be clear, in order to get full credit for question number 1 about the hypotheses, you should have some support of why you think that, using an example from somewhere else.
Yeah, right.
Okay.
Well, yeah. You don't always need a citation to support it. If you have a citation that supports your hypothesis, that leaves no doubt that it's been thought about as you're an investigator. If you don't have citation to support it, that's okay too, but your reasoning has to be well laid out. So there's some examples of that in lab 3 on developing hypotheses and the solutions to lab 3. Alrighty, so I will see you, those of you who have Monday lab. Bring your questions. Thank you.